Driverless cars may seem like a future concept, but in fact they are already working and have successfully driven millions of miles. However, for the everyday consumer, only cars with a limited amount of automation are currently available on the market. Features such as adaptive cruise control, lane keeping, and collision avoidance systems are becoming more commonplace in high-end vehicles. To clarify, lane keeping controllers intend to keep a vehicle automatically centered in its lane. Adaptive cruise controllers intend to keep the vehicle at a constant speed and a safe distance from vehicles ahead. This means that if a vehicle ahead of you slows down below your cruise velocity, your car will automatically adjust its speed. So essentially, as automakers are taking smaller steps towards completely driverless vehicles by releasing these safety features, they have to ensure that the systems that they release work properly. This is one area that the research group I am in has been working on, which is formal techniques which would produce implementations which are actually correct by construction, or in other words, they're guaranteed to work properly, which sounds pretty good. So in order to prove that this technique of coming up with a correct by construction controller is robust, we would like to see just how accurate the controller that we come up with is in practice. Our goal is to implement adaptive cruise control and lane keeping on this scaled car that I've been working on over the summer. Using the formal techniques, I can use MATLAB to come up with a correct by construction controller and then upload onto this computer. The computer will then use sensor data on the car in order to control the steering and the wheel speed in order to keep the car on a safe path and a safe distance from other vehicles. As an example, you can see here how the car responds to a change in its desired path by automatically adjusting its steering angle. Due to the complexity of the lane detection calculations, the steering response, when calculated by the UDO board, was slightly delayed, and because of this, I switched the system from the UDO board over to the Jetson TK1 embedded development board, which you can see is now mounted onto the car. With the Jetson board, I'm able to use its GPU to do most of the processing, which makes all of the onboard calculations run much faster. This is very useful for doing lane detection since it requires computer vision algorithms which are fairly GPU intensive. Essentially what happens is that I get a camera feed from a webcam, which will be mounted on the car. I then apply a canny edge detector and then the HUF transform to each image frame so that the camera can pick up the lane. You can see here that I'm using electrical tape in order to mark a lane that the camera can pick up pretty easily. Once the car knows where it is, it can apply a steering response in order to stay on the correct path.